Hi, and welcome to Module 5 of A Brief Introduction to Game Theory. In previous modules, when we discussed equilibria, we discussed almost completely equilibria in what are called pure strategies. A pure strategy is just a single strategy that you use in a particular equilibrium. So cooperate, or defect, or choose A, or B, or C, or swerve or not swerve, or stag or hare. Whatever we've been talking about, we've discussed equilibria in only a single strategy. So I play one strategy always, you play a different strategy always, and that is it. That's referred to as equilibria in pure strategies. It did mention once briefly, though, the possibility of randomizing over strategies. We discussed the idea of coordination, and if we're trying to coordinate an A and B, and both AA and BB were both equilibria, maybe we could randomize and choose A half a time and B half a time. We can extend that idea to discuss uncertainty and mixed strategies. Here the idea is there are certain things that you don't want to do all the time potentially, or maybe no equilibrium exists in pure strategies, and to find a way to get an equilibrium you have to randomize over existing strategies. So let's see how we might do that. And here's an example that's commonly used called matching pennies. It's also a very similar example to soccer penalty kicks. And it looks kind of like this. So you have a game, let's say heads and tails, we use pennies, but you can think of right or left in terms of blocking a goal. The idea is that you have two players, and one player, player 1, wants to do the same thing that player 2 does. So in this case, it's player 1 wants to have heads if player 2 has heads, or tails if player 2 has tails. In penalty kicks, player 1 wants to block. Player 1's the goalie and wants to block the ball in the same direction, has to jump in the same direction that the kicker kicks it in. Or anything else in which player 1 wants to sort of defend against player 2's actions. Player 2, in contrast, and player 1, when player 1 does not manage to defend, player 1 gets -1. And again, the negative, I could put 0, it doesn't make much of a difference. Player 2, in contrast, wants to do the opposite. So in this matching pennies game, if they both have heads, player 2 gets a -1 for having the same. Or both tails, a -1. Player 2 in this case gets a 1 when player 2 does not match player 1's strategy. So when there's heads and tails, or tails and heads, player 2 gets a 1. In soccer penalty kicks, the kicker wants to kick in the opposite direction that the goalie jumps into. Or if player 2 is the attacker in any kind of context wants to go where the defender isn't. These kind of games are generically called matching pennies, and they have this payoff structure, or a similar one. Now, what would be the equilibrium and pure strategies of this game? Let's do the same thing we did before. So first you consider the counterfactual world in which player 1 chooses heads, and player 2 chooses heads. What should player 1 do? Well, player 1 has 1 to -1, so player 1 chooses 1. And if player 2 chooses tails, what should player 1 do? Well, tails, because in both cases player 1 wants to match the strategy of player 2. Now let's do the player 2 strategies, best responses. So if player 1 chooses heads, player 2 decides between -1 or 1 will choose tails. Similarly, if player 1 chooses tails, player 2 chooses between heads and tails, that's 1 or -1, and chooses 1. And what do we get? What we get is no equilibrium in which there are two underlined payoffs. We didn't consider what would happen about that previously, but now we have to. There's no equilibrium here in which the two different players play a particular strategy. And the reason makes sense. They have exactly opposing preferences, right? Player 1 wants to match, player 2 wants not to match, so someone's always doing it happy in any kind of potential pure strategy equilibrium, and would want to change, want to deviate. So we can't have no deviation. So what do we do? Well, in cases when there's no equilibrium in pure strategies that exists, like this, what we can do is have the players randomize over strategies. They choose strategies with some probability that's less than 1 but more than 0. And by randomizing, by flipping coins or rolling dice or whatever, they generate uncertainty in their opponent, uncertainty for their opponents. And now the opponent is no longer sure what they're going to do. And because of that, we calculate expected utilities rather than just comparing utilities directly. And the goal is to choose your randomization in such a way to make the opponent indifferent. Why is that? And this is really weird. And I should say, in general, mixed strategies are the weirdest, in my opinion at least, the weirdest of all the sort of game theoretic concepts. You may be wondering, how can that be after the previous few modules? But in my opinion, they are. And here's why. Mixed strategies occur, you choose your probability of taking each action, not according to your own preferences, but according to a goal of making the other player indifferent between those players' strategies. Now, why would that be? Well, think about the nature of utility. If my utility for one action is higher than for another action, I will always choose that first action. In fact, we discussed last time, you can't even credibly commit to choosing a worse action, even though it might be better for you in the long run, because you're tied in as a rational person to choosing the action that's best for you given the options available at that moment. Well, if heads is better than tails for me, I'll always choose heads. Or if tails is better, I'll always choose tails. The only chance I have of choosing heads or tails with some probability is if I don't care which one I play. If I'm totally indifferent between playing heads or tails, then I'm fine playing heads sometimes and tails sometimes. I don't mind. It's only when heads or tails are strictly better for me will I only play heads or only play tails, and I would not be happy with mixing, with playing some probabilities over strategies. We say we play a mixed strategy, or we mix when we play multiple pure strategies with some probability each. That's greater than 0. But only when I'm indifferent between all the strategies I might mix over am I willing to play those strategies with some probability. Otherwise, I'll pick the one that's best and only play that one. So the way mixed strategies work is if we're both going to play mixed strategies, I must make you indifferent so you don't care which strategy you play and are willing to mix. And you must make me indifferent so I don't care which strategy I play and I'm willing to mix. And the sort of unique mixed strategy equilibrium that we find in that way, often unique, is going to be the strategy that makes the two of us indifferent between all of our constituent strategies. And that's weird, right? We've been talking the entire time about rationality and how I'm going to play a strategy that is best for me, and now suddenly we're proposing playing a strategy that I don't care about, but it makes you indifferent, so it makes the thing work. So that's a little odd. There are lots of interpretations of mixed strategies designed to deal with that oddness. One is these strategies occur not in an individual person, but across a population of people, and some people play heads and some people play tails, and you meet people at random. Sort of like you have a genetic code that says I will always play tails, and someone else has a code that says they will always play heads, and then you meet people and play, and you end up meeting people at the frequency that you would encounter someone playing a random strategy, the same mixing probability. I'll discuss what this means more when I go through the math. But that's one interpretation, is it's a population of people with the population distribution over strategies equal to your mixing strategies, to the difference characteristics. And then people sort of move towards that equilibrium over time. However you want to interpret this thing, though, it works the same way, and that's what we're going to do now. So the way you do this is by making the opponent indifferent between their strategies. So we're going to assign probabilities now. We're going to say that player 1 plays heads with probability P and tails with probability 1 minus P. And person 2 is going to play heads with probability Q and heads with 1 minus Q. Now, of course, Q is between 0 and 1, and P is between 0 and 1, so we have real probabilities here. Probabilities are between 0 and 1. 0 is 0% chance, and 1 is 100% chance. So, how do we do this? Well, player 2, the Q, is going to have to make player 1 indifferent between playing heads and tails. So we're going to have to write out player 1's expected utilities for playing heads and for playing tails. So what if player 1 plays heads? If player 1 plays heads, player 1 gets a 1 whenever player 2 plays tails. How often does player 2 play tails? Well, heads. How often does player 2 play heads? Well, Q proportion of the time. So the expected utility of heads is going to be 1 times the chance of player 2 playing heads plus the utility of playing heads when the player 2 plays tails times the chance that player 2 plays tails, which is this. So this is the payoff to player 1 for playing heads. And you can simplify this. That's a Q. This is a minus 1, and that's a plus Q. That's equal to 2Q minus 1. Now we do the exact same thing for player 1 to play tails. Now, player 1 gets a negative 1 whenever player 2 plays heads. That happens Q proportion of the time. And player 1 gets a payoff of 1 for playing tails whenever player 2 plays tails. That happens with a 1 minus Q portion of the time. We can simplify this, and we get 1 minus 2Q. Okay, so what do we do with this? Well, player 2's goal in choosing Q is to make player 1 indifferent. When is player 1 indifferent? Player 1's indifferent whenever the utility expected for playing heads equals the utility for playing tails. It's a 1. Now, if this is confusing for you, remember this, go back to, I think, Module 2, where we discussed expected utility and how expected utility was the sum of each individual utility for each action you take times the chance that action happens. Okay, so what does this work? Well, we have this is 2Q minus 1. That equals 1 minus 2Q. That ends up being 4Q equals 2, or Q equals a half. Okay, so now we know that player 2, to make player 1 indifferent, must play heads half a time and play tails half a time. And you see that's why it's chosen this way. The payoffs are 1 or negative 1, so you end up with Q equals 1 half, and it is indeed flipping coins. But that's not required. You could have different things than a half. So that is what we need to make player 1 indifferent. Choosing Q equals a half makes player 1 indifferent between choosing heads and tails. Now we can do the exact same thing for player 2, and we have to. So for player 2 to be indifferent, the utility for player 2 to play heads has to equal the same for tails. For heads, player 2 gets negative 1 with probability P when player 1 plays heads, and gets 1 with probability 1 minus P when player 2 plays tails. Okay. Now we do the same thing for tails. When player 2 plays tails, we get player 2 gets payoff of 1 with probability P, and player 2 gets negative 1 with probability 1 minus P. Once we do that, we can again simplify. This over here is 1 minus 2P. This is 2P minus 1. And again, you get P equals a half. It's the same equation because they're the same player in this case. So what we learned here is that player 1 and player 2, to make the other player indifferent, both must play their heads and tails each with probability 1 half. If they do this, if they both flip a coin before they play, and each player knows they're doing it ahead of time, neither player has incentive to deviate. Player 1 is indifferent between playing heads and tails, so playing heads and tails half the time is as good as anything else. And so is player 2. Both players are different over all their strategies, and so this particular arrangement of strategies playing is fine with both of them. Now you might ask again, but if they're indifferent, why can't they just easily play heads all the time? They could. Nothing's stopping them. However, the minute one of them played heads all the time, this whole thing would fall apart. And the definition of an equilibrium is when neither player has incentive to deviate, and both players are playing the best response. In this game, the only equilibrium possible is this one where each player is playing heads and tails with a half chance each. even though they could deviate, they don't care about deviating, they're indifferent, they have no incentive to deviate, they don't get better off by deviating, so this is fine, and this is an equilibrium. So in this case, both players should play half a time. Heads and tails half time. The one half, by the way, comes only from, comes basically from the payoff structure. If I were to change this to, let's say, 2 and 2, these things would differ, because now there's 2, right? There'd be a 2 over here, and there'd be a, and that'd be it for here. So we'd have, what is it, 2q minus 3q minus 1. And over here you'd have, this would be, again, this would be a 2 over here, right? You get a 2 in this time, the circumstance we're playing tails, and this would be a 2 minus, so this would be a 2 minus 3q. Okay, I'll give you the same thing again. 6, that'll be 1/2 again. So that wouldn't work. Anyway, I'll do one that's a better example in a second. Sometimes when you do this on the fly, you don't always get everything right. Okay, so anyway, that's matching pennies. Now we'll do one that has a little different structure, which is the earlier one of Battle of the Sexes, or Baka-Stravinsky, whatever you want to call it, the coordination game in which people have different preferences over outcomes. So let's do that one now here. So here you have player 1 and player 2 have two different options. And let's say that player 1 feels much more strongly about the option. So player 1 gets 3. Well, actually, you can't really compare these things that well, but let's put a 3 and a 1 here. So B has 3 and 1, and S has 1 and 2. It's a little different. So players are a little different now. And 0, 0. We already talked about that there are two pure strategy equilibria, right? But is there a mixed strategy equilibria too? Can we figure out a fair way? Because this is not fair, right? So they both want to be together in this game. But if they both choose B, then player 2 does less well than player 1. If they both choose S, then player 2 does less well than does better than player 1 instead. So what should they choose? You could say, well, player 1 cares more because there's a 3, but you can't really compare utilities in that fashion. It's just they're ordinal. The order really is what matters most. So what are we going to do here? Well, one option is for them to play randomly. For them to mix, so then both people get a chance over time to do what they want to do. So let's see how that would work in practice. So we are finishing this up. So we're going to assume that player 1 plays B with probability P, and S with probability 1 minus P, and then B with probability Q, and S with 1 minus Q. Okay, so what does that happen? So first we figure out the expected utility for player 1 to play B. What is that? Well, they get a payoff of 3 whenever player 2 plays B, which happens with probability Q, and a payoff of 0 otherwise. So we'll just leave that off. Now what's their payoff for playing S? Well, they get a payoff of 0 when player 2 plays B, so we'll leave that off. And they get a payoff of 1 when player 2 plays S, which happens with probability 1 minus Q. These must be equal to make indifference, so player 2 must set Q to make player 1 indifferent. Again, that's weird. That should be weird. That's okay. And that implies 3Q equals 1 minus Q, or Q for Q equals 1, or Q equals 1/4. So it's not a half, see? So it's not always a half, it depends on the payoffs. Okay, so now we know what Q must be to make player 1 indifferent. And you see, player 2 must play B less often than S to make player 1 indifferent, because player 1 really wants B instead of S, right? So to make player 1 indifferent, player 2 has to make sure not to play B very much. Now how about player 2? Player 2 gets this payoff for B. Player 2 playing B gets 1 with probability P, and 0 with probability 1 minus P. We'll leave that off. Player 2 gets payoff of 0 when playing S, gets a payoff of 0 probability P, and 2 with probability 1 minus P. So we get this. we must make these things equal again to make player 2 indifferent. So player 2 doesn't care what player 2 does and would be willing to play B and S with some probability. That implies P equals 2 minus 2P, or 3P equals 2, or P equals 2/3. Again, not equal to half. In this case, because player 2 likes S better than P, player 1 has to make player 2 less likely to play S by playing B more often. In this case, 2/3. Now we can change the numbers. If we changed this to a 3, we'd see that this would be 3P minus 4P minus 3. We get 3/4. We could change around the numbers by changing the payoffs, but the point remains the same. In all cases, we are trying to make the other player indifferent, so they'd be willing to play their own mixed strategy. And this is what we get for the battle of the sexes in this case. So what happens in practice? Well, we can multiply probabilities. P times Q percent of the time they both play B. So B happens 1/4 times 2/3, which equals 1/6 of the time. So BB happens, rather. How SS happens, how often? Let's see, we have 3/4 times 1/3, which equals 1/4. So S happens more often in this case. And then the rest of the time, they end up at different places. So not great. Less than half the time are they actually together to make this work. So this is not the optimal solution. It would be better if they actually went off and did stuff, potentially. But you can actually calculate the expected utility for all this stuff for one player, and I'll do this here. So if 1/6 of the time player 1 gets 3, and 1/4 of the time player 1 gets 1, and the rest of the time player 1 gets 0, player 1's utility is going to be 1/2 plus 1/4, or 3/4. Now 3/4 is less than 1, so player 1 really should be like, you know what, forget this randomness, I'll just go with U to S every time. How about player 2? Player 2 gets 1/6 times 1 plus 1/4 times 2 equals 1/2 plus 1/6, right, which equals 3/6, 4/6, 2/3. Again, less than 1, so player 2 should be like, you know what, let's do B all the time, it's better for me. So no one actually likes this better. But it's an equilibrium that in some sense is fair. If both players play it, they both get their way sometimes, and neither player cares at that point about picking either strategy or the other one. Okay. So that's mixed strategies. Again, kind of weird at times, but the main point is when you can't get a pure strategy equilibrium, there are often, depending on the assumptions in the model, a mixed strategy equilibrium available to you that you can then play, and it's useful for these cases, some of these cases in which you have players who have very opposing preferences. Thank you very much.